Okay. First of all, thank you so much for your invitation. This is my great honor to join in this seminar and to introduce my city, city of Incheon and the Incheon National University. And the topic of today's lecture is frequency domain demotic. If please allow me to introduce about South Korea and Incheon. So currently, I'm living in South Korea. This is the Korean character. So you are in Saudi Arabia. The time difference is 6 hours. So now my time is 8 p.m. So my location is very close to North Korea. It's just 30 minutes driving to North Korea, but we are separated by south and north. And my city is here, and my city is very famous for the airport. We have several airports, but international airport is Incheon Airport is the biggest. So mostly foreigners enter Korea via this Incheon Airport. And the distance between my university and the airport is 30 minutes driving. So currently, I'm here in International University giving an introduction. So this is my town, and this is the second tallest building of Korea. I'm currently I'm working in International University. We have 500 professors, and we have undergraduate students. It's 15,000 students and 2,400 postgraduate students. We have three campuses. Currently, I'm at the main campus, Songdo. So Songdo means the pine tree island. So in currently, I'm this university is in island, and there are many pine trees. So this is why this is from Chinese character. And we also have Doha campus and the Micho campus. Doha campus is relatively old, so this is an old town. Micho campus is especially for teachers. So here are some pictures of my university. Several years ago, we had offline lectures, but now for last 2 years, we delivered all online. So for 3 years, there were no students in university. But from this March, university open again. So students will study offline. Here are some pictures of graduate students. Our city, Incheon, is famous for Asian Games. I'm not sure if you are familiar to Asian Games. We have Olympic Games. This is the festival of the world, but Asian Games is for Asia. So 2014, 17th Asian Games were held in Incheon, and this is very close from my university. We also popular sports is baseball. I'm not sure if you are familiar, but baseball is the most popular. Then football. Incheon United is the second popular professional sport, and then basketball and volleyball popular in Incheon. So here are pictures. Actually, this is a drawing, not so we are here is the sea. So this side is China. So from Korea to China is by airplane only 30 minutes flight. So here is the university picture, and this is the King Sejong who created a Korean language, and this is the main building. So here are some introduction of um, um, uh, yeah, you okay. So here are introduction of my university. Okay, there are 10 universities in Korea. I mean, there are 200 universities, but mostly they are private, and the 10 national universities, including international universities. So each province has one national flagship universities. So probably some of you heard about Seoul National University. This is the top university in Korea. And my school, Incheon University, is ranking 24 this year. So there is a transportation. We can the capital city of South Korea is Seoul. So from Incheon to Seoul, it is 1 hour driving or 2 hours subway. So here is the map of subway, and this is the center of Seoul, and our area is here. So this is 2 hours train, and you can reach University of Incheon by subway. We have two names. Previously, we are called University of Incheon, but now we changed the name to Incheon National University. The reason we changed the name is to attract a high school student, because private school normally expensive. The tuition fee is expensive, but National University is only half of tuition fee of private school. So this is the end of introduction of Incheon and Incheon National University. So let me continue the today's talk is demotic and denoising in color filter array. So I want to introduce two things. The first topic is introduce what is demojaking, and the second topic is the research result of demojaking, especially frequency domain method. This is called least squares Luma chroma demultiplexing. So the goal of this talk is firstly to make a filter, and secondly, how to train and how to test. So this is quite similar process of like AI deep learning, very similar. So first of all, I want to introduce the three primary color. As you all know, to generate the color, we have to have three primary color, red, green, and blue. So my question is to generate yellow, then you need to have red and green. To generate magenta, red, blue. To generate cyan, green and blue. But this is additive color. If you draw a paint, this is a subtract. So as long you add more colors, and you eventually you obtain black. So to display like P8 this picture, then you can turn on three primary color to generate like this picture. So there are multi-chip digital camera. This is the ideal camera. To produce a color image, at least three spectral components are needed at each pixel. So each pixel must have a beam splitter and multiple chips. But the problem is that what if we have 1 megapixel image? Nowadays, there are not just the megapixel, 10 megapixel, 100 megapixel images we have. Then we have to have 1 megapixel beam splitter needed. So to then each pixel need one beam splitter, and this is not possible. So I'm sorry. Yeah. So my video is turned on again. So the alternative way to economically is a single chip digital camera. The method is like this. We obtain the scene, and there is a lens, and we have one color filter array. This is very similar to cellophane image. I mean, each pixel we accept only one color out of three. Let me recall that there are three primary colors. So each pixel accept only one, and the rest missing color we have to generate the softly or hardware way. So this is normally your mobile phone camera, mostly device accept obtaining image. We accept this single chip digital camera. Then what's the problem is that we have two missing colors out of three. So this is why most digital camera capture only one color component. Then to generate the other two color components, normally there is a color artifact. So we have to use hardware or software method to reconstruct the missing color perfectly. So here is an example. This is what our eye and your camera exactly see, but your camera use CFA. This is why only one color information is accepted, and this is what exactly the color. So as you can see, this pixel accepts only red, and the next only green, and the next only blue pixel obtained. So the goal objective is from this original image, and we accepted this image by CFA color filter array, and our goal is to reconstruct the original image as possible. And if you compare original image and reconstruct the image, and they are very similar to each other, but actually not exactly the same. So how perfectly we can reconstruct it, this is the main objective of this work. So we can use some conventional images. Let us use 24 Kodak images in this work. Especially we are using this image. This is, let's give a number, 1, 2, 3, and eventually this image is numbered 19. The reason we are using this image is this image has a vertically and horizontally high frequency area. So compared to the other images. So we are using 19th Kodak image, and here is with the name is lighthouse image. As you can see, vertically and horizontally we have high frequency area. There are several CFA patterns. This is a Bayer pattern, the most popular, and the rest are introduced by someone else. Like these are introduced by Kodak, and the rest are on paper. Some authors introduced. And the Fujifilm used this diagonal pattern, CFA. And then if we are using a Bayer pattern, so let me recall that Bayer pattern is this one, Bayer pattern. Then Bayer used two green and one red and one blue. So out of 4 pixels. So here, somebody can imagine, why not two blue? Why not two red? Why not two blue? Why two green? The reason is that firstly, green component is the most similar to panchromatic signal. And secondly, the green component, as you can see, this is the blue area, red area, and the sensitivity is green, has the highest sensitivity compared to other red or blue. So we assume green component is the more important than the other. Then we decide in 4 pixels, 2 are green and 1 blue and 1 red are assigned. Then after the Bayer CFA, the original green component, in then half of information are missing, and red quarter are remained, and 3/4 are missing. So the after the CFA Bayer pattern, then this is red, green, and blue. So what we have to do is to restore this question mark. How you can restore this question mark is we add the neighbor 4 pixels. So to restore this one GI, then we add 4 neighbor pixels and divide by 4. How about this RC, the center, is we add 4 neighbor pixel and divide by 4. And the south, this one, we add left and right and divide by 2. This is the rational. So this is the bilinear interpolation, actually bilinear interpolation. So we add 2 pixel and divide by 2. We add 4 pixel and divide by 4. So light out red bilinear interpolation shown here. Here is the result. So, and as you can see, this area and this area, there are some artifacts. This area has high vertically high frequency area, and this one is horizontally high frequency area. How about green? Because green components has twice more information than red or blue. This is why this area is relatively well restored, and this one also well restored. And the blue, you can see some artifacts shown here and here. Now we want to add RGB together. So after adding RGB, and here you can see some artifact, here artifact. And this artifact is normally we say orange color and purple color or blue color are shown, orange and purple color artifact. And this one is original image, then there is no color artifact shown here. Then our goal is how we can remove this color artifact, how we can do that. Some of you may think we want to use bicubic method, not bilinear. So here is the result of bilinear left and bicubic right. And then you can see not very different between two methods. Okay, so we want to do novel frequency domain algorithm by using RGB all together because previously the reason we see artifact in red or blue component is to restore the information separately, red with the red information, blue with the blue information. So here is the second one, and this is the spatial multiplexing model. So original RGB image shown here, and after Bayer pattern, then green component has twice more information than the other, red and blue. And if you add three components together, you can obtain this Bayer pattern CFA. Then let us assume that row number is N1 and the column number is N2. So this CFA pattern can be written with simple equation. So information of CFA is half of information of green, and with this one, and this one, and this one. So let me quickly introduce what if N1 is 1 and N2 is 1. So from this equation, from this given equation, you can add the previous one. So this one is N1 plus N2, and this one is N1, and this is N2, N1 and N2. So we can replace N1 is 1, N1 is 1, and N2 is 1. So then this will be 1 plus 1, 1, 1, 1, and 1. And after this calculation, red component will be gone. Okay, red component will be gone because this will be 0, and this will be 0. Only this will remain. So this becomes 2. So only green component remain. In the same manner, you can do with a blue component. So in this case, N1 is 2, N2 is 1. So you will replace the N1 is 2, and 2 is 1, and 2, 1, and 2, 1. And eventually, green component will be 0, and this component will be 4. So eventually, you can find CFA will be a blue component only remain. In the same manner, you can do the red. So let us rearrange the spatial multiple expression with 3 components. First one is luminant component. It means there is nothing attached. And the second one is the orange with -1 over N1 plus N2. And the third one is -1 over N1 and -1 over N2. And now we call first one is because there is no modulation. This is why this is luminance information. And this one is -1 over something. This is a modulation term. So this is the first chrominance component. And the third one is the second chrominant component. So we want to see how it look like. So luminance component look like this. This is a black and gray image. And the second one is the first chrominance component. This is very hard to see because this one has a modulation. I mean -1 over n1 plus n2. And the third one is the second chrominance component. This is also invisible because this one has -1 over n1 term, also -1 over n2 term. So frequency domain multiplexing model is calculated with this one. And now we want to apply Fourier transform because this is CFA, and probably some of you are already let's say studied -1 over something. This is Euler equation. So Euler equation is with cosine and j sine component. This is also called with expression j 2 pi something. So -1 over n2, n1 plus n2 can be rewritten with exponential component. And now after Fourier transform, we can obtain a big F and something like that, this one. So special domain CFA energy can be represented with frequency domain energy, and this is power spectral density of CFA image. So finally, so this is the final equation of RGB and LC1C2. Let me recall that L is luminance, C1C2 first and the second chrominance. So once you know RGB, then you can reconstruct LC1C2. And once you know LC1C2, then you can obtain RGB. Just give me a second. Okay. Now we want to see the different color patterns. There are several color patterns. This one, this one, this one, this one. Introduced in this image. So here are Bayer pattern. So Bayer pattern, its power spectral density is this one, which we saw. And this is power spectral density is 3D, but in 2D from above. This is the C image of power spectral density. And as you are aware, there is a luminance information has no modulation, so located at the center, and the C1 information located at the corner, and the C2 information located at left, right, and up and down. And the Yamanaka pattern, this is the main problem of Yamanaka pattern is the distance between the luminance information and its the closest the color information is closer than the previous Bayer pattern, and the distance between luminance and chrominance is near, and this is even close, and this is close to, and this is even close. So therefore, Bayer pattern is the best to make a filter. And this is Kodak pattern, and the company Kodak introduced a new CFA and introduced the W, because W is luminance, and our human visual system it likes bright than color. So we can make a compress. We can compress color information than luminance, but this is out of scope of this talk. So let me skip this one. So finally, we decide Bayer pattern is the best. Okay, so here is the main thing of the talk. So here is the step. First step, we want to extract C1 information from power spectral density, and secondly, we want to extract C2 information. But there are two candidates of C2. First candidate is left-right, it means horizontal direction. And the second C2 is located a vertical direction. So there are only one C1. So there is no option, we have to accept. But to reconstruct the C2, there are two candidates, left, right, up and down. So we can give a weight and decide which one is better than the other. And the other is automatically we can obtain. So here is the block diagram of demojaking. And in this work, we want to make a filter. So H2A, H2B, and H1. This is our desired filter. So how we can make filter design is how can we can choose H1, H2A, H2B is using by a least squares design method, and we want to change the size of filter. And so here is the equation. This is the only equation. So a CFA, this is given, and H is the filter we want to make, and this is the result of the reconstructed image after applying the filter. So our desired filter is the filter that make total square error smallest. So our desired filter is make total squared error smallest, which we call H star. So once you so to calculate this one, you want to use a least squares method, and this is the final equation of least squares method. So we have several scenarios how to design. First one is a self-training. This is impossible because we never know what's the original image. And this one, TO, training on other 23 images because we have 24 images. And this is a recommendation factor we want to recommend. Normally, this is the result of trade-off. So we want to change the filter size with like M1, M2, this is H1 size, H2A size, H2B size. So this is grid algorithm. We start from 11 by 11, and we try to reduce the filter size and to see the performance, see MSC and SCI lab performance. And here is the result of power spectrum. I mean, this is by using F frequency 2 Z. This is a MATLAB equation. We can see the filter. So the filtering in spatial domain is convolution, but in frequency domain, filtering is simple multiplication. So to obtain C1 energy, you simply multiply this filter with the CFA, power spectral density. Here is the other training on other filter and recommendation filter. And now you can see the filter size is 5, 5, 5, 5, 9, 3, 11, and 1. Previously, it used to be 11, 11, 11, 11, 11, and 1. And here is the one question is that as you can see, there are two candidates of C2. One candidate is north and south, and the other candidate is left and right. And let us consume if in this case vertically there is zero frequency, but horizontally there are high frequency. How we know is that black, white, black, white, black, white is alternatively shown, black and white. But in this case, this image, black and white shown vertically, but horizontally, frequency is zero. So now we found that if you use C2A only, in this case, horizontally, you can embrace color artifact, but vertically, perfectly, you can restore. In this case, if you use C2B, then horizontally, you cannot find any artifact, but vertically, you can have artifact. But then how you can calculate, how you can choose is that if we have a high frequency component horizontally, then you want to use C2B, but vertically, you want to use C2A. So this is the main idea. So the first scenario and the second scenario, in this case, horizontally high frequency, vertically high frequency. So how? So my idea is that we want to add the Gaussian function. So this one is horizontally, we apply Gaussian function, and vertically we apply Gaussian function. And now, then final question is how close the Gaussian function is. Previously, the center pixel is shown here, and the distance from center to Gaussian function center is 0.25, 0.3, and 4, 0.5, and I calculated and found that 0.375 is the best option. Now you can see the house, this one is totally black, and here, totally white. It means the total white area, we want to use C2B, and the totally black area, we want to use C2A. Here is the final result of the introduced algorithm. And as you can see, this is a log scale of time performance, and our proposed method is relatively fast compared to the other method, and its CPSNR is higher. And here are some previous work of my demotic method. So this is the end of the talk. Thank you for your listening.
Thank you, Professor Gwanggil, for the insightful presentation. Now we will, I have a few questions, but first from the attendees, if they have any questions, so they may raise their hands. While they prepare questions, I would like from the presentation, because for the graduate students, I think it will be interesting. You used, the frequency domain. So can we, why not like the spatial domain, or can you briefly guide us what are the the differences between the spatial domain and the frequency domain?
Yeah, thank you for your question. Actually, this is a very important question, because normally you can see this slide, right? Can you see this slide?
Yes, yes, we can see this.
Okay, so yes, as you this one, actually in this work we only consider frequency domain method, but mostly almost all other demotic methods are done by spatial domain method. Spatial domain methods are based on edge direction. I mean, to restore the missing pixel, the authors prefer to compare the difference between two directions. For example, in this case, like give me to restore here to restore this one, people try to use this direction, this direction, this direction, and this direction. And normally the best way is the difference between two pixels is the minimal one. If the minimal, the distance is if the difference is the minimal, then they assume the edge is flowing in this direction. So edge direction, spatial domain method, frequency domain method, performance very similar, but frequency domain method is relatively very fast, because this is a simple spatial domain method is convolution. Frequency domain method is a simple multiplication. Let me finally show you one more result. Here, as you can see, the other method, these all other methods are all spatial domain. Only G and F are frequency domain method.
Okay, okay, that's nice. Plus one thing more, I observed at the end of your presentation that you used the filter size of 11 by 11, right? So yes. What is the reason? Can we increase the filter size and its effect on the performance? Can you guide us?
Okay, yeah, this is a very good question. Actually, yes, I started with 11. The filter size was 11 by 11. As you can see, this is the filter size. M1's first M1 and M2, N1 and 2. This is all filter size. I started with the filter size with 11, 11, 11, 11, 11. As you can see, if the filter is bigger, then number of multiplication, it was 412. And its performance, MSc, SCI level was relatively low. So performance was very good. But as we reduce the filter size, then performance become poor. So what we can say is that bigger filter guarantee better performance. But if the filter size cannot be unlimitedly bigger, then the speed is very low. So we want to make a compromise. Here is our answer is recommendation. So RE means recommendation. So I recommend you to use this site. The filter is not very big, but the performance is not very bad. So this is my recommendation.
Nice. And one last quick question regarding this codec data set. What are the can you highlight the advantages?
Oh, this is this is very it's a very important question, because there are many images. There are many images in the world. So your question is why we use 24 Kodak images, not other images. The reason is that Demotic is originally started by Kodak company, and Kodak started in 40 years ago, 1970. They used this image to test their own product. Actually, we are working on in digital images. Actually, our mobile phone and your computer, everything was digitalized. But this images actually was taken by analog camera. So this is not digital at all. But our ancestor previously, probably your professors, also used this one. So to compare our previous method with ours, we want to use, we don't want to change the data set. And also Kodak images is, yes, you can use other images. For example, like Google, 1 million other image, COCO data set by Microsoft. You can use image set of Google, you can use others. But in this work, we don't use others. But so if you want to change other image data set, I'm afraid the performance could be lower, because this algorithm was trained only by Kodak images.
Yes, and we have some questions from our participants. So I would like to read them. You can read them as well, but I would like to read them for you. And if you could answer, I will read the first one. If you could briefly answer, this is our undergrad student, senior student, Tariq Abdullah. And he's asking, is this area of technology more focused on hardware or software? Can you briefly?
Oh, yeah, thank you very much for your question. Actually, this one, right? Hardware and the software. My answer is, as a company, as a university student and university professor, we prefer to software direct method, but company, they prefer to hardware, because once they make hardware, it doesn't cost money, right? So, and it process is, so my suggestion to you is you can make a Demotic algorithm with software like MATLAB, like Python, like C programming. And if you find the additive, the best solution, then you can make hardware. So company, they use hardware, but as we are in academia, so we prefer to use software.
Okay, nice. And we have another question from Sultan Ali Hunan, and he is asking, what could be the opportunities in the career world for knowing the difference between the domain colors? Like he's asking about like the application of this research, of this domain colors research, like finding like when you exploit the differences in these images. So he's saying, what are the job market? What are the applications for the students?
Oh, yeah, very good question. Thank you
Mm.
very much. Actually, image is everything. Nowadays, there are a lot of research areas. Somebody study sensor network, somebody study something hardware. But I'm doing image processing, and I highly suggest to you to do image processing, because image actually we can see something. Sensor network we cannot see, like communication we cannot see. And there are many deep learning method, artificial intelligence. They have many applications of image processing. You can use GAN method to change your face from male to female, female to male. Also, you can add cosmetic. So deep learning is very powerful in image processing. And like a television company, they are having a different color map. I mean, I'm in Korea, so we have two companies, LG and Samsung. Each company makes television, and normally we say LG television is more brighter than Samsung. So each company has a different secret of color generation. So this is normally we say tone, color tone. So there is a secret, so we cannot see, we cannot know until you enter the company. There are many camera companies like Japan. So different color maker, camera maker has different color property. So so uh, I hope this can be a good answer to you. So
Yes,
I highly
thank
suggest
you.
it.
Yeah, thank you, Professor Gwanggil. One last question, just quick answer, and then we wrap it up. This is from one of the attendee, and they are asking, can we use another color representation instead of RGB?
Oh, yes, of course, of course. This is a very good question. So here, here, um, uh, of course, you can decide yellow, magenta, cyan as primary color. It's up to you. It's up to you. Previously, on 19 like 300 years ago, probably Arab area is the most advanced in the world, isn't it? So
Mhm.
compared to
Yeah.
Europe, compared to any other, Arab was number one. So in that time, there was nowadays we are using RGB as a primary color, but at the time, R and G and purple was the primary color. So it depends on the area and the time. So the area of Quete, at the time, they did not use RGB as the primary. Rather, they
Okay.
use R, G, and purple. And somebody use R, yellow, and purple. So this is a very good question that
Mhm.
it
Thank.
the area and the time. So
Okay.
primary color can be changed. It's up to
Okay.
you.
Thank you, Professor Gwanggil, for your time. We look forward to more of your contributions, interaction with our students. We will look forward to learning from you. I'm thankful to all of our attendees for sparing time. It is the start of weekend in Saudi Arabia. We have Friday and Saturday, so we are thankful to them. I'm thankful to you, and with a big thank, I will close the session. Thank you so much, and thank you
Thank you
to
very
all
much.
participants.
Tomorrow is the lunar calendar New Year in Korea. So Happy New Year, everyone.
Happy New Year to you.
Happy New
Thank you.
Year.
Thank you to everyone. Thank you. Assalamu alaikum.